everybody for the afternoon session. Well, we started the afternoon session with a colloquium given by Johnstone, who have been a frequent visitor to ASIAA. But before that, he was a graduate student at UC Berkeley with French, which we overlapped 30 years. And he left Berkeley and went to CEPA at the end of 1995. And he became a faculty at Toronto for briefly before he moved to this final position where he is at now. People can read. It's a long list of positions and prestige positions. And additionally, he will talk about the JCMT transient survey, which was part of Paul's legacy with EAO. That's what will come up.
Thank you. Do I need a microphone? I don't need a microphone.
Yeah, you told us so wrong.
But I don't need a microphone, but I know that I'm supposed to be recorded. So I'll have one. It's a pleasure to be here to talk to you. I set up my visit before I knew this conference was going to happen, and as part of the visit they gave me a colloquium, which is why I am gate crashing with a colloquium in the middle of your conference. But as everything that I do, I'd like to note that I am not a student or a postdoc of Paul's. I've not worked directly with Paul, but we've been on sort of parallel courses, only I'm running quite a bit behind Paul, and I'm probably one of the slow trains, not the high-speed train that Paul is and the like. But anyways, it's a real pleasure to be here, and the talk actually fits very well with the topic of the meeting and with a chance to laud all of the cool things that Paul has done. So let me just start by pointing out 3 quick things where Paul and I have interacted. And I don't know if Paul will remember, but my first foray into observational astronomy. So I got to CETA, which is an Institute for Theoretical Astrophysics, and immediately started using a telescope because it got me to Hawaii in the middle of the winter when it's very snowy in Toronto. And we took this beautiful map of the Orion, and OMC 1, 2, and 3 were all known, and we had this region at the bottom, and I wanted to call it OMC 0 because it fit that way. And Paul was the referee, and he refused that. So I tried OMC -1, and he refused that. So that's why it's OMC 4 out of order, because I think that Paul probably had heard so many arguments from Frank about class 0 that he refused to allow zeros in astronomy. Anyway, the next big one is a meeting we had here in Taipei, spectroimaging star formation, and I was invited to the summer school to give a talk, and I met Greg Hertzeg for not the first time, but one of the first times I met him. And sitting listening to the talks at the summer school, we started asking about variability in protostars, and we came up with this idea that we really should do this. And so we put in a Herschel proposal knowing it was a great idea, and I think Paul even, suggested, yeah, you guys, you're young, you should do this. We put in a Herschel proposal and it was flatly rejected. And so then we had to decide what to do. We moved on and wrote a theory paper, which I'll talk a little bit about, on why we think we should actually be able to observe variability from protostars. And that was the situation as of sort of 2012. And then I moved to Hawaii as the associate director when the telescope was closing. It's like, the telescope's closing so we can give it to Doug because what can he possibly do wrong? But I actually had a good thing is that I knew Paul, and when we started thinking about who might be interested in it, Paul talked to us, and the next thing you know, Paul decided that there really shouldn't be a last Canadian night at the JCMT. Instead, we'll hand over the JCMT to the EAO, and Canada will continue to play a little bit of a role. And I want to commend Paul because we've played a role that I like to think we played a good role. It's been a really good match. We don't bring a lot of resources to the telescope, but we do bring a lot of knowledge and history to the telescope, and we've actually been able to build these great collaborations where I've started working not just with Taiwan, I now work with China, and I now work with Korea all the time because of the JCMT transient program. And one of the big things that Paul did on taking over the JCMT was recognize that a significant fraction of the time should go into these big surveys, certainly when the telescope was first handed over, so that again there was this opportunity for us to communicate across the generations and the communities. So thank you, Paul, for all of that. It has been wonderful, and I look forward to another 30 years of working with you. I also want to just take a pause and say, I may have done my PhD at Berkeley, but when I think of Frank Xu, I think of him firmly in Taiwan. And he brought me to Taiwan for my first visit in 1995. And Sienny looked after me that visit, writing me lots and lots of little notes in Chinese that told regular Taiwanese how to get me home if I didn't know where I was, because at that time there wasn't a lot of English around. I had a wonderful visit. I graduated that year from Berkeley. And I've had many, many visits to Taiwan ever since. If you haven't watched the video of the wonderful ceremony we had on behalf of Frank, you can watch that to understand why it is that monkey sitting on Buddha's hand and why it is that my little Alfa Romeo Spider will always remind me of Frank Xu. I'll leave that one for the coffee break. And let me now, with that long introduction, get into the talk. So, star formation in one slide. I think everybody in the audience is well aware that we think that it's gravity. We heard this morning from Luis Rodriguez about the fact that, we expected to see the gravitational collapse, but instead, when we went and looked in the early days, we saw the outflows, but the collapse is still very important. That's what brings the material down to the center. And eventually, we think we get a disk. The disk breaks up into planets. I think today we would put the planets earlier in this stage, but eventually you get a solar system. So, can't start to talk about star formation without thinking about Frank Xu and inside-out collapse. And the whole idea of the inside-out collapse model, which is something I make my first-year graduate students work through, is that if all you have is if all you have is a temperature or a sound speed, and you try to ask yourself, how do you use that in gravity to get a nice model, you get the singular isothermal sphere with a radius, with a density drops off with radius is the power of the -2. You can do all the math, and what you find out is that the infall rate should be basically constant. And half of the mass is already in the center, and half of the mass is falling in. It's a nice, very smooth model. Physics, the reality is not going to be like this, but this is a good way of thinking about what's going on. Steady state, gravity-fed, protostellar accretion. However, we know there's rotation, we know there's magnetic fields, and therefore we know that we're very likely to make a disk. Anywhere in the universe knows that, except perhaps here in Taiwan, where another conference that I was at, well after we had discovered the disks and shown that the disks were there, and all the observers knew the disks were there, suddenly the theorists came along and said, they're magnetic fields, there can't be disks. Right? It's only the theorists who can actually disprove disks after they've actually existed. What it really meant was that we needed to figure out what was going on so that we could really build the disk, how we would shed that magnetic field. But I bring this up because no matter what your model is, the material doesn't go directly to the star. That inside-out collapse model I showed on the previous slide was basically matter going down to the center, but the matter doesn't land right on the star. It doesn't free fall all the way to the star. It actually lands in a disk. And once it's in a disk, you need different physics to get it to the star. You've got angular momentum you've got to deal with. Maybe you've got the magnetic field you've got to deal with. But now you've got to move the material through, and if the disk can't transport the material as fast, the mass of the disk is going to grow. And we can go way back and recognize that if the disk gets too massive, it will get gravitationally unstable, and then it will feed material back into the star. But this is a process, and this is an unstable process. We don't expect it to be a nice, smooth process at all, even if clouds were spherical and just rotating and just had very simple colloidal magnetic fields through them. We still expect that the situation itself is going to be unstable. And in fact, my former colleague at ASIAA, Shantanu Basu, with one of his postdocs many years ago, already started looking at this, where they basically allowed the disks to grow, but not to accrete smoothly because the material couldn't get through the disk. And what they found was that they got these periods of episodic big bursts, and that the disks would go from a nice smooth state to building sometimes spiral arms, and there's also lots of clumps forming in these disks. And these clumps actually gravitationally interact and get thrown into the star as well. So Theoretically, it's well expected that there's going to be instabilities, and observationally, we think maybe the knots that we see in the outflows, and I'm not going to talk much about that in this talk, but it's one of the reasons I'm here, to work with Sieni, and to work with Sheng Yuan, and to work with Qin Fei, trying to see whether we can try to connect what's going on in the outflow to some of the infall, because if we could, we'd have a fossil record of what was happening in the accretion process, which would be very helpful to us. So, what else do we know observationally? This is a plot that was put together by Lynn Hillenbrand as part of Will Fisher's and ours chapter for Protostars and Planet 7. And all of the things in blue are different types of bursting events that you see from young stars, all the way from these giant F-Uori outbursts, which get all of the talk and none of the action, right? These are very, very rare events, but they're long events, and they may actually be the most important in terms of mass assembly, but they're not the most important in terms of what you see around you. I did my PhD at Berkeley. I'm staying in Taipei right now. I've been in earthquakes in both of those locations, and for every really big one, there's lots and lots of little ones. And that's exactly the same here, where we see all of these different types of named outbursts getting smaller and smaller in amplitude, shorter and shorter in terms of time scale, and more common as we go down. And as we said in the chapter, we still aren't entirely sure whether there's a continuum of types, whether this is really smooth or whether they are localized. Astronomers like, right? We're taxonomists. We tend to like to put circles around things and call them different classes. But it's not clear yet whether there's a single underlying. And it's not clear if the physics is the same as you go from the one process to the other. But our hope now, and what I'm going to be going after, are the objects down in this part. So they're boring. They don't have very large amplitudes. Some of them have fairly small amplitudes, but they're common. And the hope is, by looking at the common ringing of the system, we can try to get a handle on the physics of the system. This is what Frank Hsu taught me back when I was a graduate student. Look for the markers, the physical markers. Okay, so how are we going to do it? This is the theory paper that we wrote. We recognized that in the protostellar envelope, for the very young, the sources that I'm interested in, because they have all the mass to assemble, for the very youngest systems, they're enshrouded so heavily that the energy can't get out. So if you change the temperature, you change the luminosity of the protostar at the center, what it does is that energy still has to try to work its way out of the envelope. And two things occur. Basically, the SED gets brighter, and it gets a little bit bluer, right? All of the energy is coming out in the far infrared, and it gets a little bit bluer. So if I could do this the way I want to, I would have a far infrared space telescope, and yes, indeed, we are still pushing to get another far infrared space telescope, precisely because that's where the action is, that's where I want to be observing variability. It turns out I can still do it in the submillimetre, but now I'm measuring temperature. So where this would be a calorimeter if I did it in the far infrared, by looking at it in the submillimetre, I'm basically using it as a temperature probe. I'm using the submillimetre as a temperature probe, and I'm watching the change in the temperature of the envelope. And the temperature of the envelope is telling me about the luminosity of the protostar. So it turned out that with this theory paper, we were able to argue that this should be an observable effect. But it does suggest one thing I need to remind you all about is the temperature is not one-to-one with luminosity. In fact, you know, if it were a black body, its L goes as T to the fourth. So I've got a much weakening, and it's even worse in a protostellar envelope, the way the energy gets out. But it means I've got a poor lever arm in the submillimetre. So when you look and you see that my variations aren't large, remember that the underlying luminosity variation is actually significantly bigger because I have to take it to the fourth power to get, or even more, to get up to how the luminosity is changing. Okay, so one other thing we realized we needed to worry about, and that was, what is the time scale? In fact, the whole reason we went and we wanted to make the observations was, and the reason we did the theory paper, was at that same conference in 2011 when I went around and asked the theorists about observing variability, some of them told me, it can't happen. You won't see anything. The time scales are too long. And so we actually looked to see what would go on, and turns out there's no heat capacity in dust. At the temperatures we're interested in the envelope, under 100 Kelvin, the dust is pretty rigid. and it doesn't have a lot of heat capacity. There aren't a lot of modes that you can get wiggling. And so the dust heats up very quickly. Same reason why some of those very small grains get superheated when a photon hits them, right? They get out of equilibrium. So in the envelope, the heating of the envelope is almost instantaneous. So the time scale that really matters is the crossing time. And so if you're looking at something with at the photosphere, the effective photosphere of the envelope, which might be 50 AU or so, that takes about 6 hours for you to be able to see that, because you're watching the photons that have gone all these different paths through that part of the envelope. If you're looking at 5,000 AU, which is about the size scale we get to see with the JCMT in the nearby Gould Belt, that's about a month. So we went to the telescope, we went to the JCMT when they put out a call and said, we want to do a survey of these 8 star-forming regions because they've got lots of deeply embedded protostars. We can see something like almost 200 protostars in those regions. Truth in advertising, only about 60 of them are bright enough that we can actually monitor them. The other ones we're only going to see if something really bright happens. But they also have, lots of disk sources, again, in case something bright happens. And we said, we need to observe about once a month each of these regions. And that's about something like 50 hours a year. It's not a lot of time. Could you please give us the time? And they gave us a 3-year survey. They extended it by another year. They extended it by another 3 years. We're still going, and Nagiyoshi knows, even though there's not a call out at the moment, we have put in a request to continue to go for a few more years, because we're gaining huge amount of data every time we extend this, right? This isn't just getting another factor of root 2 or something by doubling. You're getting an extension in time that you've never observed, and I'll show you why that matters in a few minutes. Okay, so this is what we're doing, and I wouldn't be here giving the talk unless we'd actually found exciting results. And so here are the types of light curves that we're getting. Here are 3, of course these are 3 of our more favorite sources, but here are our sources, and what do you see that's varying? Well, the first 2 that you have here are what are called Pax bright red sources. They are sources that were found by Herschel. They weren't known to be protostars. People thought they were prestellar cores, and then they turned out to be protostars when they looked at them and saw that they actually were leaking more warm radiation than they were expected to be, but they are so deeply embedded that they weren't showing up at 5 microns or something. Spitzer didn't know that they were there. And so those are 2 of our biggest ones. And then we also found this one varying in OMC3 down here at the bottom. This is HOPS 383. And it had actually already been found back in 2015 as a burst between Spitzer and Herschel. And so what we are seeing with the JCMT is the decline of that after the burst has occurred, and now the source is declining back to where it had been previously. So these are 3 of our favorite examples. As I said, we've got something like 60 objects that we can measure fairly well, and this is a plot where we went in and we basically on the y-axis we've got the false alarm probability, and on the x-axis we have the brightness of the source, and the red ones are protostars, the blue are starless cores, and you see only the protostars are varying, and there's lots of prestellar cores that are bright that aren't varying, and if you're not colorblind, you'll notice that there are 2 blue objects up here. Those are those Pax bright red sources I just mentioned. I haven't updated this. This was our initial thing, and boy oh boy did that make me nervous when I found that I had prestellar cores that are variable, and I was very thankful when I went to Amy Stutz's catalog and found that actually indeed they were protostars, not prestellar cores. And both of them are actually beautiful, and I'll show you images of one that we're taking with Alma as we go further into the talk. So the whole thing is we are seeing these, if you look at them in this plot, 20 out of the 60 sources are varying on the time scale of something like 5 years. Okay? So that's 30% of the protostars are varying. Now the variability, if you look, isn't very high in the submillimetre, but I told you that you have to sort of do a multiplier effect to get to what the luminosity is. We're looking at things that are varying by order unity or a little bit more than that. So the variability that we're detecting right now is nothing like an FU Orionis event. It's not these big 100 times brighter or anything, but there's a factor of 2 or 3 in terms of the luminosity. So it's certainly not unimportant, right? If my salary varied by a factor of 2 or 3, I'd really care, right? So this is actually somewhat important. All right, so what's the next thing we can do in terms of trying to understand it? We don't have quite the quality of data that we'd like. You know, I almost cry when I look at the data sets that my friends looking for planets are using, right? You know, the Kepler data sets with lots and lots of data points and beautiful, beautiful error bars. But we can still go into our data set. This is one of another favorite source that we have. I'll come back to this one later. A source called EC53, which is quasi-periodic. But you can go in and you can do some type of sinusoidal fitting to it, and you can try to actually come up with a time scale that's related to the events that we are seeing. And so, you know, you've got a little bit of trickiness. Do you want to take this long time scale, or do you want to take this one? But in general, you can try to fit to the data, and you can say which is the best fit, and then you can make a plot that says what is the period for these these variables that have a time scale associated, and what is the fractional amplitude that we're looking at. And there's only this one source that's an 18-month periodicity. Every 18 months thereabout, it's quasi-periodic, but every 18 months thereabout, it goes boom. Okay? Not very high. As I said, it's about a factor of 3 or so, actually, when you go to the luminosity, but it still varies. Then we have this whole slew of objects that lie between sort of 4 and, I don't know, 12 or 13, 16, 12 years, I guess is what we marked here. And so we have a whole slew of objects that lie in here. Be very careful. We've only been observing for 5 years. So this is not a well-defined period by any stretch. It's just saying that's sort of the time scale that we're seeing is something like a decade or so. And then there are a few that are varying, that are almost linear in their variability, and those are ones that if we want to give a time scale to them at all, it's time scales of, you know, half a century or so. Again, don't trust that. We haven't observed long enough to believe it. It's just giving you an idea of, from the slopes and from the curves, how long you think these things might last. And it's really key to know that we're finding lots of them on this time scale of a decade or so. Okay, so where are they? So this is a type of plot that only a submillimetre astronomer could love, or a star formation person. At the top here is the volumetric luminosity of the source, which is telling you about the energy coming out. And along the y-axis is a measure of what the temperature of the source is. Remember, when they're deeply embedded, that it's hard to get the energy out, so it gets colder and colder until finally you get the energy out. It gets long enough wavelengths that it can get out. But this is one way of sort of looking at the earliest objects, which we call class 0. See, before other people were allowed zeros, Paul. That's just not me. And the class 1 source showing in this plot in gray in the background are basically all of the protostars that are known in the Orion region. And then what I'm showing in green and blue are the sources that are in the fields that we are looking at in Orion. And then the ones that have little circles around them, so they look like bullseye, those are all the sources that we find to be varying. So if you look at this top plot, you say, wow, all the variables are the most deeply embedded. We believe that. We believe that's true. I'll argue in a few minutes why we really do believe that it's true, that the variables are more likely to be the deeply embedded ones. But with the JCMT survey alone, you have to be more careful, because down here is a plot, same x-axis, but the y-axis now is the brightness in the submillimetre, and you can see that the brightness of the class 1s are much, much lower in the submillimetre compared to the class 0. That's because they just don't have so much envelope, and therefore these guys are much easier for us to detect. So it's a bit of a tricky game in the submillimetre alone to have the statistics to allow ourselves to really believe that it is the class 0 that are varying more often than the class 1, but I'll come back to that in a few minutes as to why we think that's really the case. Okay, so I'm going to come back. This was the slide. This is just a transition. I'm going to come back now to look at that spectral energy distribution that I was mentioning before, right? So we use the spectral energy. We want to watch, we want to monitor how things change, and here is a plot. So this is a PhD student in the UK who was working on numerical simulations of collapse of cores to make protostars. And as the core collapsed, what he would do is he'd stick a protostar in the center and he'd let it illuminate out through the messy envelope. This isn't an inside-out collapse envelope. This is a much messier envelope. And as he changed the luminosity of the source at the center, as he changed the luminosity of the source at the center from what it was originally to 5 times, 10 times, 25 times, or 40 times the luminosity, you can see how it changed as a function of wavelength. This is the ratio of the original brightness to the brightness when it was bursting as a function of wavelength. This is the actual observation, and this is just taking the ratio. And what you can see here, here's our submillimetre part, where basically you're getting a temperature effect. Here's the far infrared part, where you really do measure the luminosity change. And as you go to the shorter wavelengths, this is why it's dangerous. Not only do you run out of photons at the shorter wavelengths, but you're also, the tau equals 1 surface is wandering around as you are changing the brightness of the source, and the energy is trying to leak out. And so it becomes a little bit of a mess, or it can become a mess as you move to the mid-infrared. Nevertheless, we thought we would try, because there is this wonderful satellite. This is another one of these examples of a satellite that went up to look at the mid-infrared sky, did its job, which was basically a 2-year mission to look at the mid-infrared sky, and then was reactivated as a near-Earth object detecting device that every 6 months builds up a map of the sky, and you can see if anything happens to be coming towards the Earth. But it also has a wonderful catalog that we can use to try to look at the mid-infrared variability of protostars. So this is what we've been using. We've been using this long-lived mission at 3.4 and 4.6 microns. Oops, is this the right one? Huh, I missed the slide. That's okay. So this is what we get when we look in the mid-infrared. The nice thing is, now this satellite, we're able to look at all of the protostars in the Gould Belt. So whereas with the JCMT, we were only able to look at 8 fields, because we aren't allowed to take all of the time at the JCMT, here we're allowed to look at the whole sky. And when it comes to class 0, 1, and class 2 sources, we're looking at over 5,000 objects. And this number over here is the fraction of them, this is the fraction that we're actually able to detect, 700 out of 1,000. And we lose a few of them because they're too faint, and we lose a few of them because of crowdedness. But look at the light curves that we get. These are light curves at 4.6 microns. Some of them are going up nice and steadily. Some of them are going down. Some of them, again, have curvature. And some of them are periodic. Most of the periodic ones are background AGB stars. If you're in the audience and you like that background AGB stars, great. For us, they're For us, they're just a complete disaster, so we throw them out of the sample as best we can. But let me show you what happens when we do the statistics. So we can go in and we can say, well, how many of them look linear? What fraction of our sample are those? How many of them look curved? What fraction of our sample? Look, about 20%. That's not that far off that 30% I was saying we were getting in the submillimetre. It's a little bit lower, but you'll also notice that we have 33% are varying in an irregular way. There's a reason for that, because the mid-infrared variability is probing stuff that's happening right down near the star, and the timescales are shorter, and so it's much easier to get a mess of what's coming out. And when you're only observing it every 6 months, you just get weird data points. I suspect that many of these ones that are irregular actually have a linear or curved component underneath them. We just haven't picked it out yet from what's going on. So the numbers actually are fairly similar. Okay? And just to compare, here we are. So here was our submillimetre survey, and again, here are some of our favorite objects over here on the side. And this is the fraction that are variable if I take different cuts in brightness level. And what I really want to show you is sort of that 20 to 30%. So already we're detecting variability all the time. This isn't an FUORI event, which I only see very rarely. I'm saying, 1 out of 3, 1 out of 4 of your stars that you're looking at, protostars that you're looking at, are varying while you're looking at them, or certainly on timescales of years. Okay, this was the plot I thought I was showing you. A figure I thought I somehow got out of order. But this was a paper that Carlos Contreras painted when he was a postdoc in the UK before he came to work with Jin-Yun Lee in Korea. And what he did is he looked at a bunch of JCMT sources and Y sources and just compared them directly. And so for the same source, here was the JCMT getting fainter, here it is at Y is getting fainter. Here's another source of the JCMT getting fainter, and Y is getting fainter. And there are more, some of them are going up, some of them are going down. And what he plotted was the change in the brightness, actually the change in the magnitude from Y's versus the change in the magnitude at the JCMT, and you'll see it falls along a wonderful line that's a little bit more than 4. So if the mid-infrared was varying as the luminosity, and the submillimetre was varying as the temperature, and temperature went as luminosity, or sorry, luminosity went as temperature to the 4, you would have expected a line that was a dotted line here, with a beta of 4 between these two. We're getting something like 5 or 6. And if you actually go in and do the math, as we found is that the mid-infrared is actually a stronger than linear signal. And that's because of the way in which the envelope is. So anyways, it's a fun way of doing it and just showing you that indeed, even in the mid-infrared, we're measuring the variability. Okay, I want to give you, in the time I have left, I want to give you 2 case studies. I want to talk about this source EC53, which is a quasi-periodic submillimetre variable. I want to do a little bit about the multi-wavelength light curve analysis that we've done, and a little bit about signal time delay through the envelope. And I'm hoping that Paul will stay awake for this, because this is using the SMA and the JCMT together. And then I want to talk a little bit about HOPS 373. It's one of our PAX bright red sources. We saw it go burst. We did a bit of a multi-wavelength source structure, and we did a little bit of spectroscopy in the near-infrared to understand the shock in the disk diagnostics. Okay, so here's Young-hee Lee, a Korean graduate student who was sent to work with me for a month right before the pandemic hit, and thankfully he got out right before Canada was closed. And here he was working on what his master's thesis was supposed to be, which he turned into a very, very nice paper I consider the 2020. And so this is a quasi-periodic source, as I say. It was already known because it was observed in the near-infrared by Klaus Hodap. It happens to be near another variable, and so it was lying in his field of view. Anyways, it was already known, but it was our first variable that we found in the submillimetre sample. And let me show you a little bit more. Here's the light curve, as I say. So you can see that it's got this sort of 18-month periodicity, but it is not the same from epoch to epoch. Here is its light curve at different wavelengths. So up at the top, you have the submillimetre one, where we've got it observing from around beginning of 2016. We've continued to observe it through yet another of its pulses. And here's the JH and K band as monitored from predominantly UCURT, a bunch of telescopes, but predominantly UCURT. So in our analysis, we went in and did what any self-respecting person will do. They'll try to fit a period, and then they'll try to phase it up. And this is phasing up the J, H, and K light curve and looking at the submillimetre. And when we got this, I suddenly got very nervous because this is not what a theorist expected. So remember I told you that the submillimetre is coming from the envelope, and the envelope is supposed to have about a 1-month delay. Whereas the near-infrared shouldn't have that same delay. It should be much quicker. It doesn't have to bounce all the way through the envelope. It should be much quicker. And yet, if you look over here, you can see that the decay and the jump that's going back up, it starts going up earlier in the submillimetre than at JH and K. It's anticipated that it's going to get brighter, and so the envelope got brighter before I see the source getting brighter. And we really struggled with this because we're not optical astronomers. Well, that's not true. Greg Kirkside is in our group. But we struggled with this until we looked at the color. And this is the color of the source of J minus H or H minus K. And look how it gets red right at this phase. So in fact, what's really happening is that this is going down not because the source is getting fainter, but because the source is getting extincted. Something is getting in the way of the source as the source is trying to brighten. The submillimetre doesn't have that problem because it's optically thin to the submillimetre, but something is getting in the way when we try to brighten the source. And in fact, here is color magnitude diagram, right? And you can actually watch this thing, you can actually plot this thing up. Here it is getting fainter, and then suddenly it goes whoosh across this direction. And then we miss it basically when it gets the faintest. It's very, very quick turning around, but then it turns around and goes back up. So it's got a loop that it's doing, basically every time. So I don't want to go into a lot of the details, but there's more that we can do. This is really nice. If you plot these things, you can see that the decays and the rises always take the same time scale. They always have the same e-folding time. So you can use those e-folding times and assume something about a viscous accretion disk to try to ask yourself about time scales and therefore length scales. You can try to ask about how much material you must have. And we can make a nice little toy model that basically says that for some reason, the outer disk gets broken from the inner disk, and the inner disk basically accretes and then just disappears. And then as it disappears, and at some point as it disappears, this breaks and the material comes across again. And as this material comes across, the inner disk must puff up such that we don't see all the way down to the central source, which is why the near infrared, it continues to get fainter, even though the source is now getting brighter. So what we don't know is what's leading to the 18-month periodicity. So one option is maybe, there's some object in there that's actually breaking the disk such that the material has to build up and then get across. But we really don't know that yet, and that's where we need the theorists. So I gave a very short version of this to CETA earlier this fall, where I tried to ask the theorists at CETA if they would come and help us, because we really don't know physically what's going on. We don't have a physical model, but we do have all the numbers that we're interested in. So if you're interested and you're a theorist, come and talk to me. So I want to talk a little bit about what happens when we try to monitor at higher angular resolution. So we started out trying to do this with ALMA, but it turns out there are certain things that ALMA is really good at. There are other things that it struggles with. And one of those is giving us the cadence that we want. We can get observations with the telescope, but it's hard to get regular observations. So Dave Wilner I think you gave a colloquium, if I remember correctly, and then afterwards we were chatting and we discussed this, and you said, why don't you put it on the SMA? We can help you. And that's exactly what we did. And so this is Logan Francis here, my former PhD student. He's now working with Amin van Dishoek in Leiden. And so we did get some ASIAA data, but it's very ratty. But at the SMA, we were able to get them to trigger our observations when we noted that the source was starting to come back down and starting to come on its decay, so that we could monitor it along the whole time scale. While at the JCMT, we were monitoring it weekly. So I think if I remember correctly, the SMA data was roughly every 2 weeks, and the JCMT data was roughly every week. So that's good, we've got the data, but now we have to understand what's going on. So Logan made a toy model. The toy model has a density profile, has a temperature profile, and the temperature profile of the envelope is going to change as the luminosity changes, right? You're going to change what the base temperature is as you're going through the envelope. Luckily, a Korean graduate student had written a really nice paper trying to understand the SED of this source and what happens when it changes brightness, and therefore had a wonderful model of what the envelope profile should look like. And from our paper on the multi-wavelength analysis, we had a wonderful burst model, how the luminosity changed with every burst. So all he had to do for his PhD, for his last paper of his PhD, was put that stuff together with basically recognizing that as time goes on, so this is just showing you if there's a burst, that burst sort of illuminates the whole envelope in this funny way. This is the surface where suddenly you're actually able to see photons from this part of the envelope. Okay? And here's what he has. So here was the burst luminosity, changed into a temperature at the 100 AU in the envelope, changed into what we would see with the JCMT and the SMA. Remember, the SMA has a smaller beam, so the time scale for that thing to come into equilibrium, so to speak, is shorter than it is with the JCMT. And we took this model, we applied it, and look how well it fit. Like, it doesn't quite fit on the decay. There's something going on here, but we got this couple of week time delay between what you see at the JCMT and what you see with the SMA. And so the zeroth order, what that's telling us is we've just done tomography of the envelope of a protostar to to argue that yes, indeed, the protostar envelope does have the properties that the Korean graduate student had said from looking at the SED. And you can imagine a future, Paul always tells me we're supposed to be thinking big and thinking well into the future. You can imagine a future where you'd be able to do this by using the variability of the source to actually be able to reconstruct structure in the envelope. Okay, so the other source I wanted to talk about real briefly was HOPS 373, our PAX bright red source. This is one that we went after because it did this big jump, and then it came back down. And by the way, this is, again, monthly observations. And so you can see that the time scale actually, it did some type of a jump up, came back down, and then went up. So when I say it takes a month for the envelope to react, it's not quite that. That's what's going on. So that was a little bit of a concern. Here are observations of the light curve taken in the submillimetre and taken with Ys. And again, some K-band data that happen to be lying around. This is an ALMA image of the outflow from that source. It's a beautiful outflow. We have a paper actually in the referee right now which has a lot more detail, a higher angular resolution. There's a lot of structure in this outflow. But here's the outflow, here's the protostar. Here's where the K-band emission is coming from, right? The K-band emission is not coming from the protostar, it's leaking out of the outflow lobe that's directed towards us. Not a surprise, right? It's scattering out of the outflow lobe out here. Here's where the mid-infrared is coming from. So even the mid-infrared isn't coming from down here, it's way too embedded. This is what it means to be a PAX bright red source, is that the envelope is so thick that in order to get the mid-infrared out, you've already got to be way out in that outflow lobe. This is what it looks like in K-band. This is the molecular hydrogen spectrum of it. This is just hot shock emission in the outflow. Okay, so we think what we're seeing is, we're seeing all of this emission along these edges here where things are getting heated and you've got shocks on the outflow. We don't expect that to change as much, and in fact, when we see the two Ys bands, they don't vary with the same ratio. And we think the reason is that one of the Ys band has a lot of the H2 emission in it, and therefore it isn't changing the same amount as the Ys band that doesn't have the H2 emission. And then we went and used Igrins to see if we could punch. And remember, we're not actually looking at the protostar, we're looking at the scattered light that's coming out. But even in the scattered light, we can see the CO overtone emission. So we can see something that tells us about the disk down at the center. Okay, if you've stayed with me this far and you don't give a darn about protostars and accretion, that's fine. So I'm going to give you one last thing, which is completely different. And this was a problem that, where's Jeff? Is Jeff around? Because Jeff Bauer kept telling us that we had all this wonderful data. We should be looking for things much more interesting than protostar variability. He said, is there any evidence of anything that changes dramatically from one epoch to the next? So my former graduate student who had moved to the East Asian Observatory, Steve Maris, take a look at this. This is what he looked like as a grad student. You'll see in a minute what happened to him when he went to the EAO at Lake Hall. Anyways, he went in and he did a very quick and dirty analysis and found, hey, look, on 2016, November 20th, there was nothing here. 6 days later, there was a big bright object. Well, not big bright object, a point source object, but a bright object. And then by February, it had gone away. And a year later, this is a COVAD of all the epochs except this, showing there was never anything there. It was just one epoch. So the first thing I did is I went to see where Mars was, because I'm not really an observer and I don't know where Orion is compared to the ecliptic, but I do remember the theorists who put out a press release saying they found a supernova, only having to retract it a day later when they found out that they had just observed Mars going through their field of view. So I was worried that maybe we had a Kuiper Belt object or something going through the field of view, but that wasn't the case. This was a real brightening event. And just to show you, here's the light curve. So, la 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 la, boom, la 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 la, and it's never gone back up again. That was just a single event. Now the guys at the JCMT are really worth holding on to. Oh, by the way, this is what happened to Steve when he went to the JCMT. He went, full on Hawaiian. The reason why you want really good staff is the guys at the JCMT said, Doug, we can do better than that because your object is bright enough. We can break down that observation, which took half an hour to make. We can break it down into short time steps. And so that's what they did. And here's the source over the 30 minutes of observing. It declines 50% in brightness. Here are some other sources in that same field, just to prove to you that in fact those sources stayed the same. So this is important, right? If you've got an object that varies in 30 minutes, it clearly isn't a protostellar envelope. It's got to be a lot smaller. It's right down. It's a hot object right down to the source. What we think we're observing is a flare from a star. Okay, so this is a young star. We found a flare. In fact, we're quite excited by the fact that it's the most powerful of the flares. It's also the highest frequency, all of that. But it was a wonderful flare that we've discovered. I have to admit that we wrote a second paper where we went in very, very deep. We did a really, really good analysis. This guy was like 30 sigma, right? You could just see it. But we went in and we tried to dig down to about 5 sigma, see what we could do. We found nothing else. Well, we found a blazar, but who cares about blazars, right? We found a blazar that's varied, but we found no other flares, which is a very interesting thing, right? Because remember what I told you at the beginning about earthquakes and about accretion variability? For the big ones, you expect there to be lots of little ones. You expect there to be many, many, many little ones. And so it's actually quite confusing that the first and only one that you got was really, really bright. Now, having said that, of course, it's a sample of one, so who knows serendipity at all. But anyways, that's something that's intriguing us. So I won't go into the great details other than to say, you know, this is a really, really bright event. It's very interesting to think about what it might say if there are planets in that system. This is a class 2 source. It's a T-Tauri star. Anyway, what's next? Let me finish really quickly with what's next, and that is the JCMT Transient Survey has now been going on for 8 years or so, 9 years or so. It continues to the end of this year, but we are hoping to be able to continue it further. We recently added, actually it's not recently anymore, it's about 3 years or 4 years ago now, we added 6 intermediate mass regions that are further away. The first sets of papers on that are just about ready to be published. It's one of the reasons I'm here to work with Sheng Yuan and work that he had with a former student. The JCMT does give you 450 micron data. We have now a paper that has been refereed, and we just have to finish up a few things, which does the 450 data and does a better calibration. Didn't point out in this talk that we do a relative calibration to 1%. We're getting 1% calibration of the fluxes in the submillimetre relative from image to image because our basically systematics are so good. But the 450 data we only get when the weather is good, and we can see nice things in the 450, but it's not worth that really good JCMT time to do 450 micron work for our survey. There are other telescopes that will be better for the higher frequencies. Save the 450 data for the people who really need it at the JCMT. That's the message I think hopefully Nagayoshi has gotten. So we're planning with CCAT, which is a survey telescope primarily for cosmology, but they have a 350 micron camera that will give us the same angular resolution as 850 at the JCMT, and I have a plan to be doing a lot of observing with that, including the galactic center, to see whether anything interesting is happening. ALMA, we really decided, is more of a follow-up than a monitoring. So what we've been doing is going with our favorite objects and going back to ALMA, trying to understand what the outflows look like, what the structure of them looks like that way. And I'm putting a lot of effort into trying to prepare for a future Far Infrared Space Telescope. If you want Far Infrared Space Telescope, please come and talk to me. I don't have any money, nobody does, but I want to make sure that all of us who really care about this make it happen, because it makes you want to cry that we don't have another submillimetre or another far infrared telescope in the works at the moment, right? There's nothing at the moment. So anyways, I'll leave you then with that. We've done so much. It's the gift that keeps on giving. I want to thank Paul for basically keeping the JCMT alive. I thought I was going to shut the lights out, and I didn't have to. All I had to do was hand over the keys. And the telescope is continuing to function very well, so thank you very much for all of that. And when we put the survey in, the time allocation committee, I don't know if Nagayoshi remembers, the time allocation came back, gave us a very high grade on our original survey, and said a null result would be useful. Boy, did that take away the pressure, right? We thought that that was what we were going to get, and now it's still going, and it's only expanding as we work on it in the mid-infrared. We now start being interested in the bullets that we're seeing, in the outflows, and everything else. So thank you very much for your attention, and I'll stop there.
Questions? This is a colloquium. Yeah.
Okay, can you hear me? Okay, thank you for the great talk. And can I use the microphone? Hello, okay. Thank you for the great talk. And I have a very basic question actually. And there are two kinds of mass accretion rates. And envelope mass accretion rate from envelope to the disk. And disk accretion rate from the disk to the star. And I'm wondering, if the submillimetre and submillimetre variabilities are primarily the variability of disk accretion or envelope accretion. And for example, you showed two detailed studies, and for those cases, we see correlation with near and infrared variabilities, and that means probably the variability is due to disk accretion. But does it apply for all the anesthesies? And you also mentioned some models with missing envelope, and how missing envelope would affect time variable mass accretion.
Yeah, so if I understand the question correctly, it's about the fact that there's material falling onto the disk, and then there's the material that moves through the disk and goes onto the star. Yes. So in our case, everything we're doing is luminosity. Yes. And so the luminosity only matters that last fall, right? Because it's all the gravity, you need to get R small in order for the distance, right? So that the denominator is a tiny little number which makes your luminosity high. The material falling onto the disk on the outer part of the disk isn't dumping much energy. So we're not looking at that, we're looking at what's happening inside, just like you were talking about that infrared bit. Now, my attitude is exactly along the lines of, what drives which? It's possible that the variability in the material falling from the envelope onto the disk is changing the properties of the disk such that the disk will accrete at a different rate. But the time scales for that are very long. Right? You've got to propagate stuff from outside of the disk, which is 30 AU, maybe 10 AU in the smallest disks, but those are large scales. So I don't think that we're worried at all about what's happening from the envelope. Everything we're doing is down at the last mile falling down.
Thank you.
Yeah.
Thank you very much for this talk. So you say like so JCMT flux time variability reflects the variation in temperature of envelope. So would it be possible to mention something about how much variation is needed in mass accretion rate? I wonder how this kind of event is significant in terms of mass accretion process.
Yeah, so these are low mass protostars that we're looking at. So almost all the luminosity is coming from the accretion. So if I see a change in the temperature of something like 25%, we think, we haven't got the calibration right down, but we think what you want to do is take that 1.25 and take it to about the 5th power. And that tells you if you do 1.25 to the 5th power, you'll get something like a factor of 2 or 3, maybe as much as 4. And that's what we think the change in the luminosity is. And since we think the luminosity is all accretion luminosity, and we don't think the size scale has changed, the only thing to change is the m dot. So we think that the m dot is changing by about that much. So what you're seeing in these, in our bigger brightness events, what you're seeing are changes in the luminosity that are slightly more than order unity. So maybe a factor of 2 or 3 or 4, but we're looking at changes like that. Okay? So as I was saying before, so we think that m dot is changing by that much. So it's not
FU-ORI type. It's not EX loop type. It's not these big bursts where things have changed dramatically, but they are changing enough. If you were thinking about the physics has changed, right? Because the flow is changed by the order of what the flow was. And so that's not a minor perturbation at all.
Maya?
So, like in class 2 objects and in main sequence stuff, we have seen that some variability can also be because of stellar spots. So, do you think that, like, I don't know whether question of whether a photosphere is there in a class 0 or 1, but do we think that some analog of that can also be operating?
Yeah.
Especially for the ones which are showing much more regular kind of variation.
So I must say that I am not an expert, and so we should chat about just how big variations you can get from the spots. In terms of the bolometric luminosity, not in terms of what you get at a particular wavelength, but what the bolometric change is, right? And what are the time scales associated with those spots? Because if the spots are long lit, right, you know, we're measuring how it's heating the envelope. So it's not a question of whether the spot was looking towards me or going away. It's a question of how variable the integrated luminosity of that was over time. Now, what I will say is when you look in the mid-infrared and the like, you can see lots of short time scale events where things are falling. And you can look and you can see variability all the way to very short time scales. Because again, our envelope, we say, takes, even the photosphere takes 6 hours or something for it to smooth out, for the photons to get through to us. We basically become invisible to that, and we're only measuring sort of a smooth time. So if it is variability, again, it's the long-term measure that you get from that. Okay? But we should talk about the spots, because I don't actually know how much of an amplitude you can get long-term from the spots.
Sure, definitely we should definitely talk about this.
Yeah. I think Wei Li has a question. I'm kind of scared.
Well, since you had close engagements with JCMT and you're doing great science visits, do you see any path for Canada or other places to join back into JCMT?
Yeah. There are. So the right answer is, so I don't want to get too technical, but there is the Canadian Foundation for Innovation, which is a way for universities to get involved in, let's say, instrumentation programs and the like. And that process was used to get Canada into Scuba 2. That process has been attempted for other things, and there are professors at universities who are still very excited about the potential that the JCMT has for instrumentation. There's also, unfortunately, at the National Research Council where I am, we don't really have a master plan path to instrumentation for something where we could say the JCMT is the right place to be testing it because it's a telescope that exists. And we're running into a bit of a problem with this CCAT, where a number of Canadian astronomers, and I'm involved with CCAT as well, has sort of pulled people looking that direction. But it's a survey telescope, has a very different type of process than the JCMT does. So my own feeling from the Canadian community is you'll get a lot of buy-in for us continuing to work with the CADC and being able to provide a place for the data and the like. We can work the way we're working by helping out, but other than the CFI for some type of an instrumentation, it's really hard to see where any new money is available. It's really unfortunate, right? But that's my expectation for the time being.
Okay, thank you, Doug. Thank you, Wei Li. So last word, how do you?
Well, I was interested in the faint and fast end of the stuff. Right now, the ALMA does not give you a long cadence, but they could give you, because of sensitivity, to look at the very short time events. Right? Have you pushed that?
Yeah. So again, the concern I have is that I'm not sure that I expect much short term. We almost finding flares and that type of short term event, but my expectation is the short term events are still going to be days in the submillimetre, not much shorter than that, because I basically got to heat a zone around the object in order to be able to see it. And so that zone has a size scale associated with it, and it's hard to see things varying on time scales shorter than the crossing time. So I haven't gone that route. Where I'm really interested in the ALMA is to see when something big happens, can we see any differences? Now that we're getting these nice high angular resolution images of disks, can we see anything? Or the other one, Jinyun Lee, who I'll be going to Korea after I'm here in Taiwan, she's very interested in, can we see anything happening, let's say, with liberation of volatiles from ices, and then the length of time those will stay in, as gas before they'll get back into the ice phase. So those are using ALMA as follow-up that way. We are looking at the shorter time scale in the mid-infrared because NeoEyes takes data when it observes a region of the sky, it observes it many times for a day. And so we've got a paper actually out of the referee right now, I keep saying that. In this case, we're looking at 1-day variability in the mid-infrared versus 2-month variability that was observed with Spitzer versus 8-year variability in the mid-infrared over the long time scales to see how it's varying across those. And we see more variability on short time scales in the mid-infrared, but lower variability on short time scales compared to what we see on long time scales. So we should talk a little bit more, but I haven't found that niche with ALMA yet. I really think it's in the lines. That's where you're going to get the signal, and I'm not sure what effect I'm looking for to be from the accretion variability on short time scales. For flares, definitely, but not for the accretion.
Right. I mean, the point is that the thermal may define a certain size scale, right? But
yeah.
There may be non-thermal phenomena that you...
That's right. And so, in fact, the flares, and this is why I had Sienny was involved in our, unfortunately, null result paper, precisely because she's got models about, what could be flaring, and she won't go on the record. I think you were actually against my theory, but my theory was that maybe the magnetic connection between the disk and the star required you to have, remember my idea was maybe it required a certain energy in order for the events that we were seeing, and that might explain why the only thing we've seen was a really bright event, and there aren't a lot of things that are smaller, but Sienny didn't like that, so I'm not a good enough theorist to understand.
Let's talk.
We'll talk later,
okay.
Exactly.
Maybe you are seeing the CMEs.
Yeah.
Okay, so thank you everybody for this nice discussion. So we'll return to the regular sessions of the symposium. Thank you everyone. And thank you, Dr.